Hello students, in this video we are going to learn about motion of a charged particle in a uniform magnetic field from chapter 4. You can see the crosses that indicate the perpendicular magnetic field which is into the plane as shown in the diagram. And here is a charged particle whose charge is Q, and here it is moving with velocity V. So, it experiences some force due to the V component and also the magnetic field. And as we know that the force can be written here, the magnetic force is equal to QVB sin theta. Its magnitude can be written here as a QV by sin theta, where it is V cross B, and hence we have written QVB sin theta. And with respect to this formula, when we talk about the direction between velocity and the magnetic field, if this angle theta, in the first case I take here, if this angle is equal to 0, that means V, the velocity, is in parallel to the direction of the magnetic field. If it is in this case, then we can say the force, the magnetic force experienced by the particle is going to be 0. And in the second case, we can also say that if theta is equal to 90 degree, that means the velocity is perpendicular to the magnetic field and hence theta is equal to 90. Then we can say the force QVB sin theta is going to be the maximum force that is equivalent to QVB. At this stage, we say it is a maximum force. And we can also say that this force will continuously deflect the particle in the circular path as shown in the diagram. The force experienced by the particle, that is given by QVB, the maximum force, and that deflects the particle continuously in this circular orbit. And this magnetic force provides necessary centripetal force. Therefore, we can also write here the magnetic force, whatever is equal to QVB, that can be related here with the necessary centripetal force. And this centripetal force, which is given by the formula mv square by r, which we know already. Therefore, when we are equating this QVB, that is equal to mv square by r, comparing the two forces, we can also write the value of r, that is the distance from the center of the circular path, which is due to the magnetic force experienced by the particle. We write here r is equal to, by comparing the two equations, we come to the formula mv upon qb. This is the expression for the radius of the circular orbit covered by the particle of charge q. If this is equation number 1, we can also continue for the time of rotation or revolution of this particle. What is the time period? The time period can be given here as a t, that is equal to the total circumference covered, the distance covered by the particle, and with what speed it is covering the circular path. Therefore, we write it is the radius, therefore 2 pi r we have written, and with the velocity v. We rearrange this because we have the formula from equation 1. What is the radius? mv by qb. After substituting this, we may also get 2 pi m upon, by substituting this expression for r, we get the formula 2 pi m upon qb. This is the formula for time period. We give this as equation number 2. We also continue here to calculate what is the frequency. What is the frequency of this rotation? We write here frequency f is equal to 1 by t, as we all know, reciprocal of the time period. This equation number 2 can be rearranged in this format, reciprocal of that qb upon 2 pi m. Let this be equation number 3, which represents the frequency of rotation of this particle when this velocity and the magnetic field, they are perpendicular, and the force experienced by the particle, that is a magnetic force which deflects the particle continuously in the circular path, that is also perpendicular to both V and B here. the magnetic field. This is also called here for the devices like cyclotron. We may call this as cyclotron frequency also. For the devices which are used for accelerating the particles to some greater speed, and therefore we can say this frequency called as cyclotron frequency, having the same formula QB upon 2 pi m. We can also note a point where this frequency is independent of this path, the independent of the radius of the path, and also independent of the speed with which it is actually completing the circular path. In this expression for frequency, we do not have the formula of R, the alphabet is not there, and V is not there, and hence we understand the frequency is independent of R and V as per the equation number 3. When this initial velocity makes an arbitrary angle with the field, which is shown here, this is the magnetic field B along the x-axis, and the plane is there XYZ, and this is the velocity that makes angle theta with the magnetic field, and this velocity V is resolved into its components. One is the perpendicular component along this YZ plane, and V parallel, the parallel component is along the x-axis in the same direction of this magnetic field, and here is a charged particle with the charge Q and mass m. When this enters into this magnetic field B with the velocity V, and that is inclined at an angle theta with this B vector, then we have to discuss about the force experienced by the charged particle. Because of this, due to the perpendicular component, there is a force experienced by this, and which will be always perpendicular to this V vector as well as this B vector. There is a force experienced by the charged particle, and this magnetic force will be perpendicular to both V perpendicular component and also the magnetic field, and that deflects a particle. You can see in the diagram that deflects a particle and in the circular path which is always in the direction of YZ plane. That deflects a particle in the direction, and therefore we can also calculate what is the distance of this, what is the radius. We have already discussed about this formula. mv upon qb is the formula, and this it is due to the force is due to the perpendicular component, since the parallel component is in the same direction, velocity component. Therefore we are writing here v perpendicular in place of v in the formula for radius. This is mv perpendicular component and upon qb, and v perpendicular is nothing but v sin theta, and this is v cos theta. So we rearrange this formula, v sin mv sin theta upon qb. This is the formula for the radius of the path. We can also write here what is the time period of its revolution. Time period capital T can be written here, as we all know that it is a 2 pi r by v here. In place of that, we are writing 2 pi r upon v, the perpendicular component with which it is experiencing such magnetic force, and that deflects the particle in this direction as shown. We have written v perpendicular, and this can also be rearranged as a 2 pi r upon v sin theta. Further, we can also expand this formula by substituting equation 1 for the radius. I repeat here, v upon v sin theta multiplied by, we have m v sin theta upon qb. So we have v sin theta and v sin theta and 2 pi m upon qb, and hence I can write here this time period t can be written in the same expression 2 pi m upon qb. This is going to be equation number 2. By balancing and also substituting the radius in the expression for 2 pi r upon v perpendicular. So what we understand here, this charged particle in this case has two types of motions. This is a formula for time period. By looking at the diagram, we understand that this charged particle, because it experiences force, magnetic force, and due to this perpendicular component, it experiences force and it's deflected. But here, while getting deflected in this direction, it has two types of motions. We can observe it. One is nothing but the linear motion. It is also moving in linear along with the direction of B vector, that is along the x-axis. Another one, number 2, is a circular motion. It is also in the circular motion, that is plane perpendicular to the B vector, that is along this YZ plane. You can see in the linear way as well as in the circular way, so that the particle exhibits two types of motions. Hence, the resultant path we can say is nothing but the helical path. Otherwise, helix is represented by this particle. We can also look at this. The distance between the two circular paths, we can say that is called here as a pitch, where pitch is nothing but the linear distance travelled by the particle in the direction of magnetic field during its period of revolution. When it is revolving in the direction, what is the linear distance between this? Therefore, this is the pitch of the helical path, and we have to calculate here what is the pitch P here. That is going to be, it is the distance only. Therefore, velocity, one of the components, that is due to the parallel component in the linear direction travelled and multiplied by the time period during its time of revolution. Therefore, V parallel multiplied by the time period. V parallel is nothing but V cos theta, and multiplied by the time period from equation number 2, we can take here 2 pi m upon qb. This is called the pitch of the helical path experienced by this particle. When we rearrange finally, it's going to be 2 pi m v cos theta upon qb. Let this be equation number 3 that represents pitch of the helical path, the linear distance travelled by the particle. So this is nothing but, you can understand, the initial velocity makes an arbitrary angle with the field. Where is the field in the direction along the x-axis? The component V is resolved into the parallel component and also the perpendicular, and it exhibits two types of motions because it experiences force when this velocity vector makes an angle theta with the B vector, and due to this magnetic force, it shows linear motion as well as the circular motion. That is what given by the pitch, the distance travelled. I hope you understood the motion of a charged particle in a uniform magnetic field with the different special cases. Thank you for watching.